I'm Dr. Paris von Lockett, and today we're going to be talking about when to use a static study when you're doing analysis and simulations, specifically here SolidWorks. So there are a few guidelines that we have to follow if we're going to use a linear analysis, and that is first, the material must be linear. By that we mean it has to follow Hooke's law. You may recall from material science or solid mechanics or mechanics of materials, Hooke's law means that if we apply a force and then we measure the amount of distance something travels like a spring, then there's a linear relationship between that force and that distance, where the force is F, the distance is X, and that linear relationship is some spring constant K. So if we apply F, then we go 1 displacement X. If we apply 3F, we go 3 displacements 3X. And if F equals 0, then necessarily X equals 0, because K, that's the stiffness, isn't 0. Now, this applies to materials as well, but instead of force and displacement, we normalize things and look at stress and strain. And here, the issue is whether or not the material response is linear, and it's linear at what we call small strains. So on the left, you see a standard stress-strain curve. With this stress-strain curve, through here, we see there's a nice linear region, and if this is a metal, we'll have something like an initial yield stress, then we'll have some softening. This is if it's not worked ahead of time. Then we'll have some ultimate strength, and then finally all the way over here, some degree of failure. So our material response is linear in what we call the linear regime, which usually deals with microstrains. Microstrains are usually on 10 to the minus 6th in metals and ceramics, and they can be up to thousands of those. And in rubbers and polymers, it's a bit more confusing, but what we look at there is to say that the material is linear for as long as the stress-strain curve remains reasonably linear. And if that's the case, then we can model it as a linear material, and that'll be okay. Another caveat that has to hold is we have to deal with small deformations. Another way to put this is small motions. On the left, we see a bit of an angle bracket. There's some orange force applied to it, and it takes it from what normally would have been a right angle into something that's a little more deformed. On the right-hand side, however, we see a larger force taking this thing to a much larger deformation, way past that initial right angle. And the idea here is that the amount of deformation has to be small with respect to the overall size of the part. Now, in this class, we won't get into the mathematics of why that's the case, but for things to work out and for you to get reasonably accurate answers, those deformations have to be small, those motions have to be small with respect to the part. Next is that the loading has to be applied slowly. We call this quasi-static or quasi-statically applied. This could also mean that the loads don't change over time. Essentially, we're looking for an equilibrium case with no accelerations. So if you consider F is equal to ma, where a is our acceleration, that a term goes to 0, so we can deal with summation of forces. We can also deal with summation of moments without having to deal with rotational acceleration as well. Well, thank you for watching. Thank you for participating. Hopefully you've got a little bit better idea when we can use static analysis and when it's available to you. It's a good option. It gives good, quick results for simple problems. But for more complicated problems, we have to look at higher level analyses, which we'll do later in the course. Thanks and take care.